Hey there, so now we're going to do unit 11.4, which is Le Chatelier's principle. So Le Chatelier's principle is in relation to equilibrium. So I explained to you before in the previous lesson what an equilibrium is. So it's a reaction that goes both ways. You have a forward and a reverse reaction, and they're both occurring at the same speed, so their effects are canceling out. So what Le Chatelier says is that if we stress the system in which we find that equilibrium, the system will try to kind of fight back to regain an equilibrium. It's like an action and a reaction type of thing, a little bit like in physics. If you push someone, well, the person will try to not lose its balance and will kind of push back, right? So the Chatelier's principle is kind of about that. So we're going to look into details. Now, why do we need to know about this? This has very practical applications. Actually, if we look a little further down here, there is an example about the Haber process. So this is the reaction that allows us to produce fertilizers, NH3 over here. Now, this reaction is a reaction at equilibrium, so it goes both ways. So N2 reacts with 3H2 to form 2NH3, which is what we yield or collect in order to create fertilizers. But that molecule can also revert back into its original components. We don't want that because we want to sell this one here. So that's what we need to make. So how can we influence this process so that the equilibrium produces more NH3 than H2 and N2. So we want the forward reaction to kind of be favored in this case to make more of this, sell more of it, and make more money. So how do we control the equilibrium? Or how do we stress it so we can control which way it's going to go? Let's look at different factors. So the first one is about concentration. Now, because a concentration implies that you have something dissolved in another substance or that the volume of that substance may change, this only applies to solutions and gases because gases can change volume. So if we look at a reaction, in this case, the only substances we can play with are this one, this one, this one, but not this one. It's not that it's not part of the process, but we cannot influence the concentration of a solid because it's pure by definition. It doesn't have a concentration. So I can't play with this one. So I can affect the amount of A, B, or C in my equilibrium, in my system, in order to force the system to go one way or the other. So let's take a look at this. My system is at equilibrium presently. We tend to use the scale a lot, or the balance, because it's a very good visual tool to understand the principle. So here we have a system at equilibrium. What would happen if I doubled the amount of reactants? Well, obviously, since I have more reactants, it's as if this side is heavier. So now the system will want to fight back. It wants to regain equilibrium. In order to regain equilibrium, it needs to get rid of some of this. So it will favor the forward reaction. The forward reaction will accelerate in order to get rid of some of this and in order to basically put this even again at equilibrium. So in this case, the forward reaction would be favored, making more carbon, not carbon, but C, and making more D, and consuming A and B a little faster, then C and D are being turned back into A and B. So the forward reaction would be faster than the reverse for a while in order to get rid of the excess here. And because we're getting rid of the excess here, it's making more of these. Okay, so how does this translate in terms of a graph? So we have A versus 2B. So I have A that reacts and reached equilibrium. I have 2B, so twice as much. I'll start higher, that react and reached equilibrium. And I have on the other side 3C and 1D. So they both start over here. So I have 3C, so I'm starting at 0 at first in the reaction, but C is reacting really, really quickly because I have a lot of it. So 3C and it reaches equilibrium. And I have D that reaches equilibrium. Okay, so let's just make these longer, like this, and like this. Okay, so my equilibrium is about, let's say it was reached about here. Now, what did I do? I added more reactants, if you remember from here. I doubled my reactants. So how does this look on my graph? Well, my graph will do the following. So let's say I take my two reactants. So my reactant in blue, I increase suddenly the concentration. Now the system says, whoa, we don't want this much, so we have to kind of take out some. So the concentration started diminishing, but then reached an equilibrium again. For the other one, we also increased it. So this reactant increased, and again the system said, whoa, there's too much. Let's decrease it. So it decreased a little bit and then reached an equilibrium. Now, by doing this, we explained that we basically increased very quickly the amount of product. So your product started jumping and stabilized. And the other one also jumped and stabilized. So now my new equilibrium, appeared maybe around here type of thing. Now, two things I want you to notice. First of all, for my reactants, the line is straight in both cases because I'm dumping reactants in one shot. Right away, my concentration increases all at once. As opposed to my products are starting to be made gradually as these reactants are reacting. So it's not because I dump reactants that the products are poof, instantly made. No, my reactants will slowly react. My system is trying to adapt. And because these reactants are reacting, well, the products are being made at the same time. So they're not being made all at once. It takes a little while for the equilibrium to be reached again. Second point, as you can see, the equilibrium will not be at the same height as the previous equilibrium. So this is not at the same height as this. This is not at the same height as this. One thing I should have said before is I should have labeled my axis. This is, by the way, concentration of particles. That would make it clear. And this is time. Okay, so again, it's important to notice that my equilibrium, the number of particles present at equilibrium, will not be the same as before the stress that was put on the system. And it's normal. So in equilibrium, the new equilibrium will never be the same as before. It's important you remember that. The system will find a new balance, a new equilibrium, but it won't be the same as before. So again, important you remember that point, and also that you understand how these curves are changing based on the stress that was put on the system. Now, if we look at the opposite situation, so a little bit more practice, what if we have the reactants? What would happen then? So if I have the reactant, I have much less on this side, and by default, I happen to have more products. So what will the system do? Well, the system says there's too much on this side. Let's shift it over to this side. We want to take some of this, make it react a little faster, so we make more A and B, and we're going to try and slow down in the meantime this process over here because we don't need more of this, we already have too much. So in this case, the reverse reaction will be favored, the forward will slow down. So we'll say that the system, in order to get rid of the stress or to kind of adapt to it, will favor the reverse reaction, which in effect will create more reactants and use up some of the products, the excess of the products. So again, if we look at the graphs, what would the situation be? Well, if I draw my reactants again, so my reactants were going down, they were stabilizing, my other reactant was coming down, stabilizing, I'm probably not using the same colors, but who cares, going up, stabilizing, and what am I missing? This one was going up, let's say super high, and stabilizing. So my first equilibrium was about here. Now, how does this work? I took away some of the reactants. So let's start with those, they're more critical. So if I take away some of the reactants, I'm suddenly taking them away. So this is dropping very quickly. So the system says, whoa, there's not enough now, let's make more. So this will gradually increase and stabilize. This will drop right away, but start going up and stabilize. For the products should also drop gradually because now the reverse reaction is kind of going faster. So it'll drop gradually because it's now making more reactants and stabilize. And so that means the other one as well. My products now are being used up more quickly in order to make the reactants that we're missing. So this drops gradually and stabilizes again. So this here represents, let's just look up for a second, represents this over here going a touch faster in order to make what was lost, make up for what was lost. So that's why this gradually decreases, this gradually decreases. My two products will gradually decrease because the reverse reaction has started going a touch faster in order to make up for what was taken away. And in this case, that was the first stress. I took away some of the reactants, so this was sudden. So that's why my two reactants go down suddenly, slowly increasing again because my products are reacting and stabilizing again. So that means at some point, when my lines are about stable, that means I have a new equilibrium about here. Okay? So again, you can notice that the equilibrium is not at the same height, so I don't have, oops, sorry about that, I don't have the same concentration before and after the stress. So concentration was higher here than it is after, higher here than it is after, here the same, and here the same. And it only makes sense because in the end, I took away atoms and molecules from the system. I took away some of the reactants, so I physically removed them from the system, which translates here into lower concentrations altogether. Next, we have temperature. So for the temperature, we have to analyze which reaction is endothermic, which is exo in terms of forward and reverse. So let's pretend we have this over here, which is a system at equilibrium. Now, the forward reaction, if we break it down, will be exothermic because the energy is on the product side. And so that means that the reverse reaction will be endo, right? So these becoming my reactants type of thing for the reverse reaction, these two need to gain energy in order to revert into A and B. So that's the endo part of the whole system, so to speak. So what if we increase the temperature of the container? Now, one thing you have to get clear is that we're kind of heating up the container. We're not choosing one substance over another. We're not choosing one corner of the beaker over another. Everything is being heated up. So what we have to determine is which one. Is it the exo or the endo reaction that benefits from the extra energy? Well, if we look at the exo, the forward reaction is exo. So my reactants do not need that extra energy. That's not going to help them. But if we look at the reverse reaction, which is endothermic, that one will benefit from the increased energy. So that means that, in other words, this one is going to start going faster. And by default, this one will become slower. Not that it slows down, it's just that the other one is faster suddenly, so it makes this one look as if it's slower. So if that's the case, that means I'm going to be making much more A and B and a little less C and D if I increase the temperature of the system until the system finds a new equilibrium again. Let's look at the reverse example. What if we decrease the temperature? Well, if we decrease the temperature, let me just erase this. Okay, So if we decrease the temperature, which one are we hindering? Well, we're taking away energy. Again, this one doesn't need the energy in order to react. This one, the reverse, needs the energy in order to react. So the C and the D need the energy in order to react. Now I just got rid of the energy. So now my C and D can't react as quickly. So we're basically slowing down this process, making this one by default faster. So now I'm going to be consuming my A and B much faster. I'm going to be making C and D much faster. So these concentrations should increase, or this one I should say, because the solid doesn't count as far as concentration goes. So these two I should have more of, and this is going to get a little bit more depleted because it's going to get used up faster. So that would be the effect of lowering the temperature of the system. So that's for temperature. Now, the third factor, which is a change in pressure or volume of the container. Now, this only relates to gases because we know that we can't change the volume of a liquid or a solid. So this one here only applies to gases. And we know that when the pressure increases, the volume decreases. Now, in this case, we're really looking at pressure, but sometimes we're going to try and trick you and we're going to refer to volume instead. So you have to kind of think, okay, if I do this to the volume, what's going to happen to the pressure? So I'm going to give you an example here. First thing you need to look at, because we're only talking about gases, is how many particles of gas you have on each side. So I have 2 and 2 in total. On the reactant side, I have 4 particles of gas. On the product side, I have 1 particle of gas and 1 aqueous, so my total gaseous particles, 1. So what if we increase the pressure of the system? Which side would be favored? In other words, what am I making more of? Is it AB or is it CD? Well, the easiest way to analyze, although we're talking about pressure, is to really look at volume, because visually you'll have a better mental image as to what's happening. So, sorry, if I increase the pressure, I'm decreasing the volume, which means I have less space for my particles. My particles are cramped. They're stuck in a small area. So the system will try to limit the amount of particles present if the space available is not big enough. So what it will do is favor the reaction that will give less gas particles. So in this way, if we increase the pressure and therefore decrease the volume, the forward reaction would be favored because it only yields 1 particle of gas versus 4. Again, the system's trying to get rid of the particles of gas because there's not enough space available. You can, if you want an analogy, you can think of a party. So if you have a big hall, you can invite more people to your party. If you have a small hall, you'll have a smaller wedding, for example, less people present. So it's the same thing here. The smaller the container, smaller the hall, the less particles you can have or the less guests you can have. If the hall was really big, so if I had a very high volume, which means I would have a low pressure. So if I have a high volume, a big hall, I can invite more guests. There's more space. So in this case, I would be making more of the reactants. In other words, the forward reaction would be favored if I had a bigger volume. So bigger volume, more space, more particles can be present. Which reaction, sorry, this is reversed. Which reaction would favor this side, would make more of this? In other words, it's the reverse reaction that would make more of this. This one, the forward, would be favored, making more C and D if I have a small volume, so not much space available, or a higher pressure. So small volume, not much space available, I have to stick to the smaller amount of guests or gas particles, and the reaction that makes that is the forward reaction. So that's the one that would accelerate momentarily to reach a new equilibrium because I changed the size of the container. The last factor, it's really a non-factor, it's the addition of a catalyst. Now the catalyst, what it will do is affect both sides equally. So if I had a forward and a reverse that were occurring at the same time, I'm adding a catalyst, a positive catalyst, let's say, well, both are going to speed up, but they're going to speed up equally. So basically they're still canceling out. So it really doesn't have any effect on the actual equilibrium. So now, as a little review, let's take a look at this. So we're going to go over concentration, temperature, and pressure all at once. And if you're able to fill out a table like this on your own and get it all right, you understand the whole principle. So my change here is an increase of C. I'm increasing the concentration of C. What does that mean? There's too much C. So my system wants to get rid of it. It'll favor the reverse reaction to get rid of it, which means that ultimately this will go down. This will go down because they're being consumed, which will translate into an increase of B and an increase of concentration of A. So that's the first example. Okay. Now, what would happen if I decrease the concentration of B? Well, the system says, oh my God, there's not enough. What am I going to do with this? There's not enough. I need to make more. Which reaction will make more? It's the reverse. If the reverse speeds up or is favored, this will start going up again. So at the same time, because I'm trying to make more B, the concentration of A will increase. And to make this, what's reacting? These two. So this is going down, and this is going down because they're being used up. Okay, what if I increase the temperature? If I increase the temperature, it's always the endothermic reaction that will benefit from that because I'm putting more energy into the system. Now, is it the forward reaction that's endo, or is it the reverse reaction that's endo? In this case, it's the reverse reaction. So again, by increasing the temperature, I'm putting more energy over here, which benefits the reverse reaction. So the reverse is being helped. And that means that these two are going to be consumed faster. And these two are going to start appearing faster. Then they will be used up. What if I decrease the pressure? Well, that means I'm really increasing the volume. If I increase the volume, I have more space. The system can accept more gaseous particles. On this side, I have 1 plus 2, 3 gas particles versus 3 plus 1, 4 gas particles. So in this case, more space, more gas particles. The forward reaction will be favored. So I'm going to be making more of C, more D, and I will be consuming, or the system will be consuming, more A. So this is going down, and the concentration of B is going down as well. So again, if you understand this and you can do the exercise on your own, then you've mastered Le Chatelier's principle. See you in class, or see you next time for another episode. Bye.